if we had the differential equation a times y double prime plus b times y prime plus c times y equals a function times f of x, and a, b, and c are all constants, then this is a constant coefficient, second order, linear, and non-homogeneous because of this non-homogeneity, f of x. If I told you to solve this, we might know how to solve the homogeneous case where instead of writing f of x, we wrote 0. But this is less interesting if we actually really do want to solve the case where it equals f of x. And as we know, to solve the non-homogeneous case, the general solution to the non-homogeneous case, y sub g, equals the general solution to the homogeneous case plus the particular solution to the non-homogeneous case. So what we can write this as is the general solution to the homogeneous case plus the particular solution to the non-homogeneous case. And this particular solution, what it tells us is we don't need extra constants. We just need one single solution. And how might we find this solution? We can find this one solution with a method built for finding a single particular solution to constant coefficient non-homogeneous second order linear differential equations that can actually also extend up to higher order. And this method is the variation of parameters. Variation of parameters. What is the variation of parameters? I'm writing it big so you know it must be important. The variation of parameters says, okay, let's say you already have a general solution to the homogeneous case. Your general solution to the homogeneous case, so the general solution to the homogeneous case, is equal to a constant times a particular solution to the homogeneous case, plus another constant times another solution to the homogeneous case. What the variation of parameters says is that there will be a solution to the non-homogeneous case of the form, instead of c1, you have a function v1 of x times your first solution, plus another function v2 of x times your second solution. The variation of parameters guarantees that for the right arbitrary functions, v1 and v2, this will be a particular solution. This will be what we're looking for over here. Okay, great. But what are these functions v1 and v2? They're just arbitrary functions right now that we're saying must satisfy this to make a particular solution. What are they? Well, what we can do next is pretty sneaky. I think it's almost cool. And we're going to solve for v1 and v2, so I'll show you how to do that. But before we do, you can almost imagine that we're playing out a card of hands. So we have a hand of cards, is what I meant. And out of this hand, we have, obviously, our hand is these two functions, v1 and v2. We have two jokers, though. So we have a joker over here and a joker over here. And what I mean by saying these two jokers, because I know it's a math video, not a poker video, is that we have two trump cards, two arbitrary constraints that we can say, because v1 and v2 are an arbitrary function, we can impose two arbitrary constraints on them. In general, this will work. So if you have two arbitrary functions, we have two arbitrary constraints. Obviously, once we use up both arbitrary constraints, these functions will not be so arbitrary anymore. They will be well-defined. But in a way, that's what we want. We want a well-defined function that will find us a particular solution. So as we go through this derivation, remember our trump cards, because we're going to use both of them. So the first thing is, I'm just going to say, if this is y sub p, is this v1 of x, and really this should be an arrow also, because it's not equal, it's going to be an arrow. It shows that we can get to this form. Let's just plug this in and see what we get if we plug this into our differential equation. All right, well, obviously the first step, as we know, is we're going to have to differentiate it twice to find what yp prime and yp double prime are. Okay, so if we have this, so we know obviously zeroth derivative. That one's pretty easy. And I'm going to stop writing of x. So just y1 times v1 plus v2 y2. The first derivative is going to equal, we do need to use the product rule because these are both functions of x, v1 prime y1 plus v1 y1 prime plus v2 prime y2 plus v2 y2 prime. I will say that this is going to be a lot of me saying v1 y1 prime, prime. It's going to be a lot of primes. It's going to be a lot of derivations, so you might want to skip ahead if you don't want to see all the derivation and just understand why it works. But it is nice to see the derivation, especially because, you know, we're going to get to play our trump cards, our jokers. It's going to be so much fun. All right. Now, if you can imagine, this is yp prime. If you can imagine what would happen if we took yp double prime right now, what would happen is we would have two problem areas, because this term and this term would give us, out of the product rule, we would get one of these guys, and then something, and we would get one of these guys, and then something, which is to say that we would get second derivatives of our arbitrary function. We don't want second derivatives of our arbitrary function, because if we got second derivatives of our arbitrary function, we would have to solve a second-order differential equation to get our arbitrary function, and that's what we're trying to do anyway. It would be an infinite loop, and it wouldn't be good. So what we can do before we try to calculate the second derivative is play our first joker, play our first trump card, set our first arbitrary constraint. Let's write it that way. Set first arbitrary constraint. Arbitrary constraint. All right, and we're doing this so that we don't get second derivatives, so that it is, this is for no second derivatives. V2, V1 double prime, V2 double prime. What we're going to say is simply that V1 prime times Y1 plus V2 prime times Y2, this must equal 0. It is a definition, because I'm writing it with that colon included, that V1 and V2 are defined such that they satisfy this property. Okay, great. Now, let's continue. And what we have to remember now, one of our arbitrary constraints, we just used it. The other arbitrary constraint, in a way, says, all right, this has to be true. We also need it to actually satisfy that it makes a particular solution. So you can think, even though now we've already played one of our arbitrary constraints, so this one's, it's played, we also, our arbitrary constraint, our other one, is also already kind of used, and I'll show you what I mean later. So that equals 0, which tells us that we can rewrite our particular solution, yp prime equal to v1 y1 prime plus v2 y2 prime. Fantastic. Now if we take our second derivative, we get no second derivatives of the arbitrary functions. We get v1 prime y1 prime plus v1 y1 double prime plus v2 prime y2 prime plus v2 y2 double prime. Fantastic. Now, if we were to add all of this up, what would we get? But the following, which is that we have, I'll try to use different colors to make it clearer. Oh. A times yp double prime. So v1 prime, y1 prime, plus v1 y1 double prime. And this is going to, by the way, probably be the most algebraic part of the entire video. So if that's not what you're into, again. But it's still going to be fun because we're going to show some cool stuff. All right, and now we're going to add on b times yp prime. It's going to be v1 y1 prime plus v2 y2 prime. And now plus c times yp. So many rhymes. It's fun. This must equal 0. And now you can see that when we're saying equals, we're actually, what we're really saying is not just that this equals 0, but that we're defining, again, the colon for definition, we are defining v1 and v2 such that they must make this equation true. Okay, so let's see what we can do with this now. If we were to do some clever factoring, well, what we can show is that we get, so let's just do two steps. Let's multiply everything out, and then let's refactor. Okay, so what do we get on the first time? We're going to get a v1 y1 prime plus a v1 y1 double prime plus a v2 prime y2 prime plus a v2 y2 double prime. So I just did the a term plus, I don't know why I'm cycling colors like this, but b v1 y1 prime plus b v2 y2 prime. Let me do this a little bit lower so it's a little bit neater. Plus b v2 y2 prime plus, and now c times v1 y1 plus c times v2 y2. And I don't know why I did it so that we were shifted one away from the color we were really doing. This has no significance that I just decided to randomly shift colors here. It's a bit odd. And okay, now we have quite a mess of an equation, but we can do some cool stuff with it. And what I mean by do cool stuff with it is we can factor things nicely. Okay, let's see how we can factor it. First, notice that we have some nice terms here. We have, so excluding, so don't worry about this term with a v1 prime or this term with a v2 prime. Excluding that, what we see is we have the following. An a v1 y1 prime. We have also a b v1 y1 prime and a c v1 y. If we factored out a v1 here, we would get something nice. And also, we have a v2 y2 prime, b v2 y2 prime, and c v2 y2. Again, if we factor that out, we get something nice. So first, let's deal with the terms that we don't that aren't going to turn out nice, which is these ones highlighted in red. So a v1 prime, y1 prime. So basically, the ones with the derivatives of v. This is going to turn into a v1. I guess we can factor the a out. So a times v1 prime y1 prime plus v2 prime y2 prime. All right. And now we can start doing what's cool, which is factoring out all of this. So let's factor out a v1 from all the purple terms. And we're going to get a y1 double prime plus b times, whoops, not the v1, y1 prime, first derivative, plus c y1. What we notice about this is that we said that y1 is a particular solution to the homogeneous case, which means that this equals 0. Because it is a solution to the homogeneous case, when we plug it into the homogeneous case, it spits out 0. This equals 0, so this entire term just goes away. And now, if we look at what happens to the next term, a very similar fate befalls it. We factor out an a, sorry, not an a, v2. I don't know what's going on with my brain right now. And we get a times y2 double prime plus b times y2 prime plus c times y2 equals 0. Oh wow, y2 is a solution to the homogeneous case. This is going to also equal 0. This also equals 0. So this entire term, similarly, it's gone. And what we're left with now is, and I think I'm out of space on the bottom, so I'm going to, well, actually, no. I am highly mistaken. There's much space on the bottom. Never mind. What we can say now is that our final constraint is that a times v1 prime y1 prime plus v2 prime y2 prime, that this must equal 0. Again, bring back the definition, like this should be keeping here. So it's still all just definitions. So what we say now is, and wait a minute, I must have made a mistake somewhere along the line. Well, since when was this equaling 0. Okay, just to be clear, we're solving the non-homogeneous case. So when I wrote out that when we plugged it into the differential equation here, this shouldn't have been equaling 0. This should have been equaling f of x. My mistake. I'm sorry. So this is equaling f of x, f of x, f of x, defined to equal f of x, which tells us the following about v1 and v2, which is, namely, that the derivative of v1 times the derivative of y1 plus the derivative of v2 times the derivative of y2 must equal, which I guess we don't really need the colons anymore, we're just going to say equal in the sense of algebra must equal, f of x divided by a, the coefficient on the y double prime term. And now if we consolidate what we know this, we know that, and I guess I'll clean it up slightly by erasing nicely. We know that, and we also know this first condition here, that v1 times y1 prime plus v2 times y2 prime, we know this must equal 0. That was one of our arbitrary constraints. I'm going to move this down one more time, actually. So if we have these two constraints, these can define for us our function. So these two constraints, they define v1 and v2. So this is the definition of v1 and v2. Definition of v1 and v2. It's algebraically defined, but that's fine. And what it tells us is if we could solve for v1 and v2, what would we get? Oh, and I've made another mistake also. This is v1 prime, v2 prime, and the y's don't get their derivatives here. Just going back to this property, it's v1 prime y1 plus v2 prime y2, not v1 y1 prime plus v2 y2 prime. It's v1 prime. Okay, so this is the definition of v1 and v2 algebraically. If we know this definition, we can say, all right, whatever v1 and v2 might be, after solving this, what we can say is that v1 times y1 plus v2 times y2, it must be a particular solution because we solved it as such. These two constraints guarantee that v1 and v2 are particular solutions. So if I move this slightly closer here, whoa, I got two of it. Whoops, anyway. So we guarantee both ways. So if it is a particular solution, this is guaranteed. If this is guaranteed, it's a particular solution. Perfect. And just as a quick side note, when is this equation solvable? In general, if you have a system of equations with some variable, which in this case, the variables are v1 prime, and v2 prime. You can imagine varying them until you get the correct function. The variables times whatever your other thing is. The equation is solvable if the determinant of the other thing is non-zero. And that's a little bit from linear algebra, a little bit of high school matrix stuff. But if you have, if we have the determinant of all of our coefficients in a sense, which are these y1s and y2s, so y1 prime, y2 prime, if this determinant is non-zero, does not equal 0, then you will have, we have a particular solution to the non-homogeneous case. I'll write it in red because it's so important. To the non-homogeneous differential equation. And that's pretty cool. And just quickly also, if you wanted to use algebra, you could do your algebra, use Cramer's rule, whatever you wanted, to solve for v1 prime, v2 prime, and once you had that, you would take the integral, you would get v1 and v2. And this is the method of the variation of parameters. Thank you, and I'll see you in the next.